Okay, we are now continuing with integrals. And now we're going to look at some applications of integrals. Probably, well, at least in this class, the main use for integrals is going to be determining the area under a curve. That's one of the big uses of integrals, and that's going to probably be the main thing we're going to do in the remainder of this class. So just to give so if we have just a traditional graph here, and say we have some kind of a function, sometimes what we need to do in math is determine the area between the function and the x-axis in this case. So what we want to do, or what we need, is to determine that area. And later on, we'll even do some problems where we have like two functions. And then sometimes they want us to find the area between the two functions. To solve both these problems, we're going to use integrals. What I'm going to do in this short little talk is try and give you a pretty high level idea of how integrals can be used to find the area here. I'm not going to give a super in-depth presentation, but just a little feel for what's going on. And then obviously I will do some examples of the kinds of problems you're going to see in the homework. Now, eventually we're going to use calculus to solve these problems, but sometimes for special situations, we don't have to use calculus. Sometimes we can use old-fashioned geometry to find the area. So for instance, very simple, straightforward example. Say if I have a function equal to 3, if you want to, anytime you have f of x, you can replace it with y. So think of a function or a graph y equals 3. Well, what is the graph of y equals 3? Hopefully you all know. But that's just a horizontal line. That goes to the value, and y is 3. So maybe they ask for the area of f of x equals 3. And then a lot of times what I will do to make it very clear, sometimes I will say and x, and I'm going to write x as an interval, like from 1 to 4. Although just beware, sometimes when they give you these problems, they won't say x equal, they'll just say the area between f of x equals 3 and from 1 to 4. What they're really saying is when x goes from 1 to 4. So here's 1 and here's 4. So we're looking at this right here. Of course, what is that? That's, I guess in this case, it's a square. It could have been a rectangle. Turns out it's a square. But whether it's a rectangle or square, we can use basic geometry to find the area of this rectangle, length times the width. If I call this the length, maybe 3, and maybe I'll call this the width, 3 times 3, this area is 9. And what that translates into is if we were to break this up into sort of squares, right? Each square is 1 by 1. So this is an area of 1, another area of 1, right? We have 9 squares, which means the area is 9. All right. So to find the area of this, we didn't use any calculus, we used geometry. Matter of fact, here's another one. And I'm doing these because you will have a couple of problems like this in the homework, I believe. How about we make it a little more interesting than just a horizontal line? How about I draw a diagonal line, and just to make sure I get it straight, let's do like this. As it turns out, the equation of this line should be x plus 1. So they give you this function and they say find the area underneath this function, underneath this line, and from 1 to 4. Now, once again, what they mean is x going from 1 to 4. 1's right here, 4's right here. So it's almost like they're wanting to know this area. Well, once again, I can actually determine the area of this by geometry. Now, what I'm going to do, some people might use like some kind of trapezoid rules, but I'm going to actually just break it up into a rectangle and a triangle, right? So the area of the rectangle, right, we'll call this our rectangle. Once again, this side is 2 and this is 3. 2 times 3 is 6. The area of this rectangle is 6. This right here is a right triangle. If you remember, the area of a triangle is 1/2 the base times the height. If we look, the height here is, well, the base, I guess we do base first. It's like the base is 3. The height is 2. 1/2 times 3 times 2 equals 3. So the total area is 6 plus 3 is 9. And if you were somehow able to sort of figure out the areas of this, and try and add up all the little parts of squares and stuff, it would equal 9. So there's 2 examples where we figured out the area under a curve or a function by just using geometry. Of course, those only work for very basic kinds of curves. What if you had something like this? I don't know of an equation that I can use in geometry to figure out this area. It's not really possible. So then that's the big question. What do we do when we have something like this? Now, I'll take just a couple quick minutes and give sort of the philosophy of what happens. So let's just do like we did here. Let's just do some kind of a sort of a curve or a wavy line. And let's just say, you know, from 0 to 8. So we're going to try and find that area. Well, I don't have an equation for this shape of an object from geometry. So here's what they did in the past, even hundreds of years ago. They said, why don't let's break this up into rectangles where the width, in this case, I'm gonna make the width 1. So it's almost like I'm gonna go to 1 here. So I'm gonna start along my left edge, and let me just draw it, then you'll see what I'm doing. So I'm going to, actually, just to make it look decent, let me draw it, and then you'll see why I'm doing what I'm doing. So let's just go from maybe here to here, and then from there to there, and then maybe from there to there. This isn't going to be perfect. From there to there, and then from there to there, then from and then from. All right, so what I've done, I go here at 0, and I go to my curve at 0, and I draw a straight line across, and then I'm going to draw, and then I go to the value of 1 on my function, and then I draw a line across. What I'm doing is, well, this one I messed up on. This one should go from here to here. And this one should go from here to here. So what I'm doing is I'm sort of breaking up this area into a bunch of rectangles, right? And so the height of the rectangle is defined by sort of the left side of the rectangle, the function. So at 0, I'm right here. I just go across to where x is 1, and I stop, and then I make a rectangle. At 1, I go to my function up here, and I go across, and I stop at 2. And then now for 2, I start here once again on my curve, and I go to 3. So what I've done, I've basically broken this up into 8, 1, 2, 3, 4, 5, 6, 7, 8 rectangles. Now these rectangles are all the same width. In this case, it's 1, but normally when we do calculus, we would just call that delta x. There isn't always a width of 1, could be anything. And the idea is, now I know from geometry how to calculate the area of rectangles, right? Length times the width. So what I can do is I can calculate the area of this first rectangle, and then the second rectangle, and then the third and the fourth. I can add up the area of all 4 of these rectangles. And what I'm doing is I'm assuming that the area of all these rectangles is sort of kind of going to be close to equaling the area under the curve. Now it's not perfect, right? Because look at this rectangle. There's a little bit of area that I'm not accounting for. But then when I get to here, my rectangle has a little bit too much, and here it's too much. then I get over to here and my rectangle is not quite big enough. So that's why it's an estimate, right? So it's a pretty good way to sort of get close to the area. And as a matter of fact, in a minute, we're going to calculate a problem like this. It's sort of a pain because you have to do a calculation on every single rectangle. If I was to actually do this problem, I have to do like 8 different calculations and add them all together. But here's a theory behind this principle. Here, I decided to break this up into 8 equal rectangles. What if I were to, instead of breaking it up into 8 rectangles, I would break it up into 16. So I sort of cut each of these in half. So now this one, maybe, I don't know if you can see, I should use a different color. I don't know if it's going to show up on here. Or let me see what shows up. This is like a blue pen. It may not show up as blue. Oh, that's pretty good. Let's do it. So the blue pen, I'm going to break this region up into 16 rectangles. So I sort of would go here and then here. Whoops, I didn't do that correct. It should be here. And then here. And then here. And then here. And then here. So I'm doing the same principle, except I'm doing it twice as many times because my lines aren't very straight, so I apologize. And maybe you can't see it here very well, but what happens is when I make my rectangles narrower, there's less sort of overlap and there's less, mistake in here. Matter of fact, let me show you. We're going to do this problem in just a minute. So here is a problem where they broke it up initially into 4. So here's my function. They broke it up into 4 rectangles, and you can see here, always there's some overlap. So this is going to be the mistake. Like, look here, how much extra this rectangle is outside. So if we were to calculate the area of these 4 rectangles, then it's going to be sort of close to the area under the curve, but there's a lot of sort of slop in here, right? But what they do, they take the same shape, and now they, instead of having 4 rectangles, they do 8. And then look here, up here, it's pretty good. Now there's still some extra over here, but if you would add up the amount of overlap in this one and the amount here, it may not be totally obvious, but this is sort of a better representation. Matter of fact, then if we were to take this and to split it up even more, then the more rectangles we split it up into, the closer each rectangle gets to the actual curve. And actually what happens is, now this is where the calculus comes in, and this may or may not make sense. What we do is we turn this into a limit problem. If we could make the width of these rectangles as small as possible, let me just sort of, I just want you to see what's going on. So say I make my rectangle here super skinny, and then the next one, super skinny, and then super skinny. When I make them skinny enough, as I'm drawing these rectangles, it looks like these rectangles are almost tracking the actual curve. When you make the rectangle so wide, it gets off the curve pretty easily. But when you make the rectangles so narrow, it sort of tracks the curve, because every time you turn around, you start a new rectangle. Well, what would happen in a theoretical sense if you made these rectangles so small, you can't even, what if it's almost like the rectangle is so small, it almost looks like a line. It's so narrow. So it's almost like each one of these is like a rectangle. And what happens? You can see with really, really narrow rectangles, it's almost tracking the actual curve. So if I can make these rectangles super, super skinny, super narrow, and then add up the area of each of these individual skinny rectangles, then that area is going to actually be the area under the curve. So the whole key is you try and make your rectangles as narrow or as skinny as possible. The skinnier you can make it, when you add up all the area of the rectangles, it's going to be pretty close to the actual area under the curve. Matter of fact, what they do mathematically is they do this, where they try and make this delta x, the width of the rectangle, they want it to approach 0, right? The limit as the width of the rectangle approaches 0. It never quite gets to 0, but it gets super, super close. So when you do that, that whole principle, I won't go over it here. We do math with this. And when you do this kinds of thing, it ends up creating an integral. And then the integral ends up being the area under the curve. So the calculus comes in anytime we're doing limits where something is approaching 0. Do you remember for the derivative? You remember what our derivative definition, that ugly, the limit as h approaches 0 of f of x plus h minus f of x over h. Remember this difference quotient? What did we do? The limit as h approaches 0. This caused it to enter the world of calculus. When we take the limit, well, this limit here causes it also to be part of calculus, except up here, this thing's a derivative. When we do what we're doing here and you do all the math, it ends up being an integral. I'm not going to take the time to give you all the other details. You can actually look at it in the book if this kind of thing interests you. I tell you this because they're actually now going to give you some problems. It's almost like, if you remember when we first did derivatives, we did it using this equation. It was painful and a lot of work. And I even told you, you do this a few times and then we learn all these shortcuts and you never do them again. Well, it's almost the same thing with integrals. They're going to give you a couple of problems where they're going to actually make you add up the areas of each of these rectangles by hand. And then you do these few problems and then you'll never do them again because we end up just using all the rules we learned about integrals. So let me actually do one of those kinds of problems. So this is the kind of problems you're going to have in the homework, at least a couple of them. And I admit they're a little bit painful, but I guess they want you to suffer through it and then you can figure it out. So here, they've actually, here's the function for this curve, square root of 4 minus x squared. So that's the, it's like y equals square root of 4 minus x squared. For that equation, this is what it looks like. They're wanting to find the area under this curve, right? From 0 to 2. So they decided to break it up into 4 equal width rectangles. And what they're going to do now is they want to find the area of each rectangle and then add those areas together. And then they're going to see, they're going to estimate that that's the area under the curve. Now you can see it's not going to be quite right because, like I said, you can see there's some extra part of the rectangles outside the curve, but it's our first guess. So the key to doing this is, first, you have to know, even though it's called f of x, just to make it very clear, I'm going to write it as y equals 4 minus x squared. So what I have to do is I'm going to label these like R1, R2, R3, and R4. And my job is to calculate the area of these 4 rectangles and then add them together. Well, I know the width of the rectangles are all the same. They're all 1/2. The key is going to be what's the height of the rectangles. Now this one's pretty easy to see. The height of this first rectangle is here at 2. Now here's how, you notice what happens is when you do this rectangle, the left side of the rectangle is right on the function, and then the right side is usually off. So when you get to the next rectangle, you notice the rectangle starts right on the function, and then as you move a distance of 1/2, of course, it gets off again. But then the third rectangle starts back on the function, and here. So you know what I need to do? I need to find, if I want to find the area of this rectangle, I know the width is 1/2. I need to know this distance here. Now this first one's easy, but what you do is, we need to be able to do it mathematically. What I need to do is, I need to, in a sense, figure out these 4 points. Because these 4 points are the 4 heights of my rectangles. I need to know this number here. I need to know this number here to figure out the area of this rectangle, and this one here. Now this one's pretty easy, but what you do is, for rectangle 1, right, rectangle 1, what is the value of x on the left side of my rectangle? Right up here, x is 0. I need to find the value of y. What do? I put in 0 into my equation. Y equals 4 minus 0 squared. That's square root of 4, it's 2. So I know my first rectangle, the height is 2, the width is 1/2. So right away, I'm going to say the area of rectangle 1, let's write it like this. Area of rectangle 1 is 1/2 times the height, which is 2. The area of this first rectangle is going to be 1. Now let's go find the area of the second rectangle. Well, I know the width is 1/2. What's the height? Well, it's this point right here. Well, what's the y value of this point? I cannot really tell from the graph. That's why I have to use my equation. So here for R2, x is 1/2. When x is 1/2, what's my y going to be? I plug it into this equation. Y equals 4 minus 1/2 squared. 1/2 squared is 1/4, so it's almost like 4 minus 1/4. Now in this case, I'm going to start using my calculator, because 4 minus 1/4 is like like 15/4. For this problem, we're not going to give an exact answer. So in this case, now I'm going to grab my calculator. I'm going to say 15 divided by 4 divided by 4 equals, and the square root of that is 1.936. 1.936. So I'm saying the area of rectangle 2. Now, you know what? Oh, you know what? That's not the area. That's the height. That sort of makes sense, right? Because the first rectangle had a height of 2. The second rectangle is just a little bit less, 1.936. So now the area of rectangle 2, the width is still 1/2. I'll call it 0.5. And the height is 1.936. So 1.936 times 0.5, 0.968. So the area of rectangle 1 was 1. The area of rectangle 2 is 0.968. And that sort of makes sense because, you know, this second rectangle is just a little bit smaller than the first rectangle. All right, 2 rectangles to go. So once again, same routine. I know the width of rectangle 3 is 1/2. How do I find the height of this rectangle? Well, the height is this point right here. That's where x is 1, and I go to my equation, the function, and I plug in x equal 1. So I plug in 1 in here for x. 4 minus 1 squared, 4 minus 1, square root of 3. On my calculator, square root of 3 is 1.732. That's the height of my third rectangle. So the area of my third rectangle, once again, the width is, the width of the rectangle is always 0.5. And the height is 1.732. And that's 0.866. Area of rectangle 1, area of rectangle 2, area of rectangle 3. So like I said, this is not that hard once you sort of see what's going on. It's just tedious. It's just a bunch of busy work. So for the last rectangle, once again, my width is 1/2. I need to get the height of the rectangle. That means when x is 3/2 or 1.5, I plug it into the equation and I find the value of y here. So y minus 3/2 squared. I'm not going to even simplify that. I'm just going to do my calculator. 3/2 is like 1.5. So 1.5 squared, make it a negative, and I'll add it to 4. So this is actually square root of 1.75. 1.32. 323. That's now the height. And it looks about right. Look, I'm saying 1.3. Here's 1. 1.3 is about right. So now the area of rectangle 4 is, the width is 1/2. The height is 1.323. (0.661). So I've taken the time now to calculate the areas of these 4 triangles. Now I just add them up. So 1 plus 0.968 plus 0.866 plus 0.661, 3.495. So that's I almost call it an estimate of the area underneath this curve. I know it's not quite right because it's obvious from looking at it. That's the kind of problems you're going to have to do in the homework. A couple of these. Like I said, it's a little bit tedious, but now what's interesting is, like I said earlier, the narrower or the skinnier you make the rectangles, the more rectangles you have. And the more rectangles you have, the more accurate your calculation becomes. So because the book did this problem, we can look here. So with 4 rectangles, that's the area. So we did it correctly. What happens when we go to 8 rectangles? Once again, because the rectangles are narrower, there should be not as much extra rectangle outside the curve. Now, just so you know, the book did the calculation. When you do 8, it's right here, 3.40, 3.340. So that's with 8 rectangles. This is 4 rectangles. Now, just for fun, they went ahead. Let me grab the book real quick. They went ahead and actually figured out the actual area. I can tell you what it is real quick. The actual area is going to be, let me find it in the book. Is 3.142. So you can see the first one, 3.495, the actual 3.14. So it's like a pretty big gap there. The next one, it's closer, right? 3.34. So the area dropped and it's getting closer to the actual. And if we were to keep doing this and went to 16 rectangles and then 32, every time it would get closer and closer to this. The good thing is, after this homework assignment, you'll never do this kind of thing again, because this is not the best way to find the area under a curve. Instead, we're going to use calculus. And just for fun, I didn't plan on doing this, but just as sort of a sneak peek, what if I solve this problem with calculus? So with calculus, let's see how much work it is. Actually, you know what? I'm not going to do it because I'm going to get over my head. Integrals aren't always the easiest things to do. And this one, I'm worried if I start it, I may get myself in trouble. Since I didn't prepare for it, we'll just stop there. But this is the principle, and you're going to have some homework problems like this. So hopefully now that you've seen me go through this in detail, you'll know how to do the homework. So, all right, let's stop for now. And then the next video I'm going to make is actually doing all these kinds of area problems using actual integrals.